Okay, in this video, we are going to look at the reactions of amino acids and how to make amino acids. Okay, all right. So the reactions of amino acids are really just the reactions of amines and the reactions of carboxylic acids, which we've all had before. So let's just look at a few examples of some of the more popular ways to make amino acids. Okay, this first method here, is called the Gabriel synthesis, okay? And in the Gabriel synthesis, you've seen it before, we are adding a nitrogen anion to an alkyl halide and doing an SN2 reaction. It's just that the original Gabriel synthesis actually was designed to make amino acids. So here's the real Gabriel synthesis, or the original Gabriel synthesis here. So we're going to take an alpha halo ester and this potassium thalamide right here, and we're just going to do an SN2 reaction, and this is going to produce the adduct, and then we're going to take this group here, which is called an imide, and we're going to do a hydrolysis on it. There's our hydrolysis conditions, usually just basic conditions, and this is going to turn the thalamide into the alpha amino acid. Okay, another method is the Strecker synthesis, which is really very similar to something you've had a few weeks ago. That is the cyanohydrin formation, except now we're going to, instead of using hydrogen cyanide, we're going to use ammonium cyanide. Okay, and when we use ammonium cyanide, we get this alpha amino nitrile here. So an aldehyde reacts with a ammonium cyanide to produce the alpha amino nitrile. And you can really think of this as just being the nitrogen analog or the imine analog of cyanohydrin formation. All right? When you hydrolyze this under acidic conditions, you get the alpha amino acid. The cyanide group hydrolyzes to the carboxylic acid group. And you have to use the acidic hydrolysis, because if you use the base hydrolysis, you'll just turn the compound back into its starting material. So we're going to treat an aldehyde with ammonium cyanide followed by H3O plus in heat, and this is going to produce the amino acid. And this is known, again, as the Strecker synthesis. Okay, all right, so here's the mechanism for it. There's not really a mechanism, it's more a play-by-play. We're making the aminium salt, and the aminium salt is more reactive to the cyanide than is the starting aldehyde, and we end up with the alpha amino nitrile. Okay, our next synthesis here is called the acetametomalonate synthesis, and it's really based on something you've had before again, the malonic ester synthesis. Okay, so we're going to take this compound right here, which has the elements of malonic ester or diethyl malonate, a compound we looked at when we were looking at how to make substituted or how to do substitution reactions in the alpha position. The only difference here now is that it's also carrying this nitrogen group along with it. Okay, so when we go through the standard operations of the malonic ester synthesis, we're going to pull the proton off. Okay, and this will give us this intermediate anion. Okay, and then in the second step, we're going to do an SN2 reaction. As long as we can do the SN2 reaction, we can make this CC bond right there. Okay, then we're going to do the standard operations in the malonic ester synthesis. We're going to hydrolyze the ester. This conditions here are a little different than what you saw with the malonic ester synthesis, but it's designed to do the ester hydrolysis, hydrolyze each of those ester groups, and hydrolyze the amide group here as well. Okay, and this now gives us initially the compound that has two carboxylic acid groups and an NH2 group. I'm just drawing it here without doing the proton transfer, but once you heat this, you're going to lose one of the carbon dioxides, just like you did in the malonic ester synthesis, and this is going to produce the alpha amino acid right here. Okay, so this overall process is known as the acetamido-malonate synthesis. Okay, we're going to look at the reactions of amino acids, and like before, they're really the individual reactions of carboxylic acids and the individual reactions of amines. A lot of them are incompatible with the other functional group, but I'm just going to highlight two of them that are going to become important later when we talk about protein synthesis. Okay, so if we subject an alpha amino acid like this one, this is isoleucine. If we subject that to the conditions for the Fischer esterification, we're going to turn the carboxylic acid group into the ester group. Okay, so it's just like any other carboxylic acid in this case. Okay, since it's now the ester instead of the carboxylic acid, there's no extra proton to transfer. So the NH2 group is just going to be NH2, neutral. And of course you have to not heat this too high, because then you can start seeing a reaction between the amide and the ester. Okay, another important reaction here is amide formation. Okay, so under slightly basic conditions, of course, we're going to generate the anionic form of the amino acid. And once we have this, we can now start turning this NH2 group into the corresponding amide. Okay, all right, so if we treat this with an anhydride and KOH, you kind of have to have these together all there at the same time. Recognize that if you had the KOH in this here all by themselves, of course, you'd just turn that into the carboxylic acid. But as long as the amine is present here, you're going to turn the NH3 group, basically the NH2 group we generated by the initial process is going to convert into the amide derivative. Okay, one of the more useful amide systems is the T-butoxy carbonyl group, and this has the abbreviation BOC. Okay, so that unit all by itself is going to be called abbreviated BOC, and that's the BOC group. All right, this reagent here, this fancy anhydride, actually has a kind of a cute name. It's called BOC-ON, and its purpose is to put a BOC group onto a nitrogen. Okay, all right, so we're going to take phenylalanine in this case, or any other amino acid really, except probably lysine, and we're going to treat it with BOC-ON, and we're going to convert the amine group into the amide group. And this is actually the BOC esters tend to be abbreviated as just the amino acid, then the dash BOC, amino acid abbreviation followed by BOC. Okay, all right. And so those are common reactions that you've had before. We're going to look at one reaction that's totally unique. This is the Ninhydrin reaction. All right, and this is characteristic by its purple color. Notice how I have drawn the product of this reaction as a deep purple, and that's the exact color of this, and that's the symptom that this reaction has worked. All right, so what we do is we're going to take this compound here. This is called Ninhydrin. It's an example of a rare stable hydrate. It's going to react with an amino acid, and we're going to make an aldehyde. Carbon dioxide is a byproduct, and we're going to produce this purple stuff right here. Okay, and this is important reaction for protein labeling. If you ever watch CSI and notice them spraying this stuff that's going to turn the fingerprints purple, this is the Ninhydrin reaction. When they become purple, they become more visible. Okay, and so this is a common technique in forensic chemistry. Okay, as long as a protein of any type is present, you'll see this reaction occurring. Okay. All right, so what happens in the Ninhydrin reaction? Okay, so this is a stable hydrate, and it produces this compound here. Now, the central carbonyl group right there is very unhappy because it has all these electron withdrawing groups destabilizing it. So this very rapidly reacts with your amino acid to generate now the imine functional group here. Okay. And this is going to lose carbon dioxide through the arrows that you see here to make this imine that we have here. This is now going to hydrolyze. The imine group is going to hydrolyze to this compound, and it's going to produce the aldehyde as a side product. And this compound that now has the free amine group is going to condense with another molecule of Ninhydrin to generate the purple stuff there. It's really just an imine formation using this amine right here as the source of the nitrogen part of this molecule. And since this is not derived from an amino acid, it doesn't have that COO8 or that carbon dioxide leaving group. So this purple compound is now a stable compound. Okay, so that's where this video is going to end. The next one we're going to start talking about peptides. These are compounds that contain more than one amino acid unit in them.